Um, Good afternoon and welcome to Introduction to Shader Authoring. My name's Tim Cooper and I'm an editor-developer at Unity. I've been in the games industry for a few years now. I've worked on such titles as Bioshock and the soon-to-be-released XCOM. And you also may know of me from the Strumpy Shader editor. I'm just going to pass over to Sean now.
Cool. I'm Sean. I'm also an editor-developer at Unity Technologies. I've been there for a little over a year now. Oh my god, I got really loud. I come from more of an indie background, but before Unity I worked at a company called Flashbang Studios, and I was a shader authorer back then, so that's where I have this shader background coming from. So let's get started. So about a year and a half ago-ish, Aris, one of our lead graphics guys, wrote this blog series called Shaders Must Die. And in this blog series, he kind of just ranted about how shaders were just terrible. And one of the things he really brought up was that shaders just have the wrong abstraction level. This whole vertex fragment program thing and all these various problems with shaders written traditionally. Programs, supporting different platforms, handling shadow, casting, receiving, lighting models, deferred rendering, forward rendering, etc. It's just a pain in the ass. And so what he came up with was the base of what we have now, and this is what we call surface shaders. And in surface shaders we have all these repetition and complexities abstracted out. There's a single program instead of having two like vertex fragment programs. There's no lighting model calculations, shadows and projectors are handled automatically for you, and different rendering paths are automatically handled for you. As a quick example, on the left there you have, this is the shader the diffuse shader that we shipped with Unity 2.x. Notice the scroll, 378 lines for that, and that's the one we shipped with it. And then as comparison, this is Unity 3x. Grand total 27 lines. And this even supports deferred rendering. So it's like, well, yeah. We needed this. Even for our sake and anyways, off to Tim.
So how do you use surface shaders? To start with, it's probably best to give a bit of an overview on ShaderLab. Now, ShaderLab is unique to Unity, and it's used by every shader. It's essentially the glue that ties the shader code to Unity. So as you can see, surface shaders exist inside of ShaderLab, and they're in fact a subset of everything in ShaderLab. So we're going to start by just looking at an old style vertex-lit shader. This is actually what still ships with Unity because it's a fixed function shader essentially. So as you can see, we have a shader. It has its name specified at the top. This also specifies where the shader or material lives in the material dropdown. Underneath that, we have a properties block. These expose the properties that you would see in the material inspector. So in this example, we've got some colors and some speculars and some textures and that kind of thing. Inside of that, we have a subshader. Now, only one subshader is normally executed upon rendering, and it's executed depending on certain rules. One of them is support level. So if you've got an old level sort of hardware, it won't execute the first, it'll use the fallback or something similar. Inside of a subshader, you have tags. These are essentially key value pairs which are used for matching on rendering. That's a little bit outside the scope of this talk, but we use them internally for quite a few things, for shader replacement and the like. The next thing we have is the pass. A shader can have multiple passes, so you could have, say, an overlay effect that's rendered as transparency on top of a normal shader or on top of an original base pass. But in surface shaders, we basically replace the pass block with a surface shader. Now, here we have the simple built-in diffuse shader in Unity. As you can see, it has the standard ShaderLab glue around the outside. So we have the properties and the subshader and the fallback specified. But inside, we also have a CG program block. Now, this CG program block essentially forms the basis of the surface shader. The first thing it has is a pragma section, which tells Unity that it's a surface shader with some other rules. It has a section of uniforms, which are values that the shader can use. It has an input structure, and this input structure is passed from the vertex shader to the fragment shader. and it has a surface block, which is the meat of the shader, which has all the interesting parts about how you're illuminating or how you're shading your surface. It also has a surface output structure, and this is what's passed to the Unity lighting functionality. So you fill this function out describing your surface, and then Unity handles it afterwards. So going through each of those blocks and breaking it down into a little bit more detail, we have the Pragma surface block. Now, this first part of the block tells the Unity that you are writing a surface shader. The second part is the function name for the surface shader that you're using. In the previous slides, you saw that we actually had a function called surf. And then finally, there's the lighting block. And this block is the model that you're using. In these examples, we're just using the built-in Unity lighting models. In this case, it's the Lambert block. Uniforms are just simply types. They have they do not change from pixel to pixel or even vertex to vertex, but they can change between draw calls. These are declared by you, so you put them in your shader. Unity actually fills them out for you. So if you have some properties that have a default color, or you've changed your material and overridden these colors, Unity will fill these out for you so that you don't have to do anything yourself here. They have a type, so in this example we have a sampler 2D, which is a texture, and we have a float, which is just a simple vector 4. The name should normally match the properties unless you're doing something silly, or unless you're doing something a bit more advanced. We also specify an input structure, which is passed from the vertex to the fragment program. This has these change per vertex, and they're interpolated over the pixels. These are also declared by you and defined by Unity. So in this example, we have the main texture, the UV for the main texture, which is modified per pixel. That has a type and also a strict naming convention, which in this case of UVs is just UV and then the name of the texture. Then you have the surface program. So we're actually going to go into a lot more detail later. So this is an overview, by the way. This is the meat of the shader, and this describes everything you want to do, and it provides the data to the lighting model. You fill out the output structure, and then, as such, this is the output structure itself. And this is the default Unity output structure. It has the albedo, which is the surface color, the normal, which is the normal you wish to use to render, an emission, and then specular, gloss, and alpha. Yes, so this is used to pass data to the lighting model. You don't actually have to specify all of these. You can only use 2 or 3 if you feel like it, depending on what you want your surface to do. And now to the interesting part of the talk, the demos.
With all the pretties.
Yes.
All right, so let's kill this and then make this work again. Okay, how do I do this? Oh, there you are. There we go. Okay. So first we have this color material, and obviously it's changing the head of the soldier to green. So let's just take a closer look at this material. So this is actually simpler than the diffuse material that the diffuse shader that we were looking at before, but it has all the same elements. The first part for Shader Lab, and the last part for the fallback. And then we have this CG program here. And inside that, we have the compilation directive saying that it's a surface program. And then we have the surf, which is saying this is going to be the program that we need to run for the surface program. And then the Lambert lighting model. And then we have this input structure. And if you look closely, we actually don't use it anywhere in the surface program. And this is just because that we need to have some data, or some dummy data inside the input structure, because the input structure needs to exist. This is kind of a weird limitation inside this surface program, or how we handle surface programs. But there just always needs to be an input structure of some sort, even if you don't use it. So in this specific one, we fill the albedo with a float 4 of 0, 1, 0, 1, which is green, with an alpha of 1. So if we go in here and just change this to 0 and then change this to 1, it'll turn them red, like so. So let's, this really isn't that useful because it's not exposing anything to the material inspector. So if we take this and drag this material in here, you notice that we actually have a color control inside the material inspector now. And if I click on this, I can change the color of his head now and everything like this. So let's take a look at this shader. It's very similar to the old one, to the last one. Now we have this properties block defining the color. So this is the actual variable name or the uniform name that we're going to be using. This is the string that's used inside the material inspector. This is the type that we want to use. So this actually tells the material inspector what kind of control it needs to be used here. And then the default value for this color. And then down here, we have the uniform added. And it just needs to match the same name as the one we created in the property. And then instead of defining a new float for, we just pass that on to the albedo directly. So if we go hop over here, and we can just see that working magically. So let's add a texture to this. So now we have a texture. And if we edit this guy, instead of the color block, or instead of the color property, now we have a main text property. Again, the string literal. Now we use 2D, which means it's going to be a texture. And we're defaulting the texture to white. So if the texture reference is null inside the material inspector, then it just creates a white texture for the shader to use. And then down here we have the same uniform, but now it's just a sampler 2D instead of a float 4. And now we use this text 2D function. And this is the first time we're actually using the input structure. This text 2D function, you pass it in a UV and then also the texture, and it'll get spit back a color back to you. And in this instance, we're using the input structure UV for main texture. And this is the strict naming convention Tim mentioned earlier. The strict naming convention for this is prefixed with UV, and the last part just needs to match the name of the property in the uniform. So notice it matches main text, and then the first part's UV, and then Unity will just fill out what the UV is for this specific texture. So we just pass that in and get a color out of it and pass that into the albedo. And that's what would create this. So let's add some normal maps to this guy. So now you can see that he's kind of angry. That's what normal maps do. So yeah, and it's basically copying the exact same thing we did with the main texture. We have a bump property now with normal literal. It's a texture, and we're defaulting it to a normal default, which means that if it's null, then that means the texture won't modify the normals of the surface at all. And then we have a UV bump for the input structure, noticing that the bump name is the same as the uniform, and a new uniform sampler 2D. And then down here, now we're filling in the normal part of the surface output structure. And if we go scroll. On develop, use correct amount of size, there you go. Now we have this text 2D, which is exactly the same, but we have it inside of an unpacked normal. And this is necessary because Unity packs normals in interesting ways depending on platform and depending for various reasons to save size and performance and other reasons. And this is decoding that data and pushing it onto the normal. It's just something you always have to do when dealing with normal textures. And that is passed on to the normal. So now I'm going to pass this off to, oh no, one more for me. Specular color. Just to iterate some more. Go to the specular. Now we have a specular, which is a float. And you notice that there's a range here, range of 0 to 1. This means that it'll have a nice slider in the material editor to goes from 0 to 1, and won't allow it to go outside of that range. Gloss, another float, and then we have spec color. And then down here, the input structure is the same, and then we have uniforms for specular and gloss. And you may notice that there is no uniform spec color. And that's just because, for whatever reason, somebody decided that we should be defining spec color ourselves. I don't know why. So whenever you have spec color, that exact name right there, spec color, just remember that it's defined by us already, and the uniform is defined by us already, declared by us already, and you can just use it at any time.
The lighting model is also different.
Oh yeah, and the lighting model here is different. So BlendFong is used whenever you want specularity on your surface material. And if you want to learn more about the differences between lighting models, Google is your friend, and there's documentation about it on the Unity website. And then we just pass the specular and gloss onto the thing. And then the lighting model calculation actually looks directly at the spec color. So now I'll pass this on to Tim to continue.
Yes.
I'm sorry, is the sample file up online anywhere that we could pull it down?
The shaders?
I mean, this file that you have with all these shaders written out.
No, it's not. And if you were at my talk, at our talk yesterday, I keep on saying that yes, we'll put it up after every talk that I say, and then I forget, and so people just bother me on Twitter. The Twitter thing is only going to be at the end, and I'll remember to do that.
Yes. So now we're going to look at a simple cutout example. Now, as you can see here, if you look at the side of the soldier's helmet, it actually has a hole in it now, shaped like a spade, right there. Now, what you can do is you can actually choose to discard parts of material based off some arbitrary rules. So we're going to go and have a look at how you would do that. So as you can see here, we now have a cutout shader, and we specify this alpha cutoff range. This is simply defined like before. It's just a cutoff between in a range between 0 and 1. And we've also actually changed the tag slightly. It now lives in the alpha test queue. If you want to find out more about the queues where certain things should live, it's actually all documented in the ShaderLab documentation, the queues that we have internally. And there's just the render type has also been changed to transparent cutout. So it just tells Unity when it should render this material in its rendering queue. One thing we have also changed to support cutting off of materials is we've added this alpha test parameter here. What this does is it takes a variable to use for doing the alpha test or the clipping, and in this case it is the cutoff value. So what this basically says is that any time the alpha that you are writing out is less than the cutoff value, which in this case by default is 0.5, don't display that pixel at all. So if we go down, we can also see that we actually write the alpha value out now as textureColor.a times the color, which is just a passed-in color. So if we go back to the soldier and we slide this alpha color around, if we slide this down below 0.5, his head will disappear because we're basically cutting off anything below 0.5. So quite simple. Yes, so that's quite a simple cutoff example, but let's look at something a bit more exciting. So the reflections are something that are pretty important to a game. If you use any sort of shiny surface is much improved by using some form of specular cube map reflections. So what we're going to do here is, this effect is a little bit overblown, but as you can see, if you rotate around, he has a sort of reflection of the sky reflecting off him based off a cube map specular reflection. Now let's have a look at how you would do this in Unity. So just looking here, the first thing you can see is we have a reflection cube map specified, and in the shader, this is done quite easily by specifying a cube type. This is just a cube map. So if you, just like there's a 2D texture type, we support a cube texture type. It has a name as before and a display name. And over to the right, it has a default value, which is in this case is underscore skybox, which means that it'll use the skybox that is configured on the current camera during the rendering. And it also has a text generation type. This is a little bit more complex, but what this is essentially saying is that this cube map is going to be used for cube map reflections. So generate all the UV coordinates and that kind of thing in the cube maps in a way that will work with cube maps. So going back to this part, we've added a sampler cube, and all we do is, into the input structure, we've also added this next built-in value called world reflection. What this does is it gives you a reflection vector on a per pixel basis that is the camera view reflected off this character into space. So for this, we use that value, we use that reflection vector to look into the cube map and get the color. Then we just simply set that as the emission color. So that's one of the reasons it's quite bright, because we're emitting quite a bright value. So as you can see, once again, if we rotate around, the reflections change based off the view angle because we're using a reflection vector. Now, if you look at this, you may notice that the reflections are actually quite sharp. So there's no real sort of distortion based on normal mapping or anything like that. So instead of using the interpolated normal for the reflection vector, it makes a bit more sense to use the normal as created from the normal map. So we have the next example here, which, as you can see, it sort of changes it actually changes the normals and the reflection slightly. If we rotate around, you can see that it's a bit more accurate because we're using especially on the headband area here, the specular sort of moves in sort of stripes because it's using the normals from the normal map. This is a little bit more complex than the previous example, but this is a bit more complex than the previous example, but it's not too bad as well. So we specify the cube map like we did before, exactly the same, but we've also added in the normal map here as a bump type. If we have a look, we specify the bump UV like we did in the previous normal map examples, but we also have this magical type here called internal data. This works differently depending on which inbuilt pass is being used, and it's a little bit out of the scope of this talk, but what it basically does is it provides a way for Unity to translate the normal from the normal map into world space so that you can use it for things like reflection. And all we do is similar to before. We unpack the normal and we pass that to the normal, obviously, for the normal mapping. But we also use that value as a world reflection vector. And this constructs a world reflection vector using the input surface structure, which contains the internal data, and the normal as decoded from the normal map. So this translates the normal map normal into world space. We then pass that world reflection vector into the cube map and then pass it through. It's a little bit complex, a bit more complex than the previous examples, but unfortunately, due to the way the surface shader system works, this is the only real way to get a normal into the correct world space without doing some seriously hacky things. Yes, is that all? Yep. So we actually got quite a bit of time to actually go through questions because this is a pretty brief overview, but we're sure that there's a lot of things people have to ask about this, and we always spend a lot of time answering questions about shaders. So yes, you, first question.
What happens if you took off internal data? What would happen?
It would fail to compile.
We can do that as well. Let's have a look.
Just to prove me wrong.
Yeah. So there we go. It should fail to compile. Yeah, there we go. It's because the world reflection function actually uses internal data to do its calculations, and the variable doesn't exist.
Well, when it turns purple, it just means that the shader failed to compile, and that's just a fallback shader. Internal data, it's more of a learned thing about when you should include it, but it's used for converting matrices or converting world space to tangent space, tangent space to world space for normals. Yep. And it's if you need to do that, then you use internal data. Sorry?
The question was, does it hurt to always include internal data? And that's actually a very good question. So as you see here, we have an input structure. The input structure is passed between the vertex and fragment programs. There's actually a limitation on graphics hardware, and only a certain amount of data can be passed between a vertex program and a fragment program. And this actually changes depending on Shader Model 2, Shader Model 3, or DirectX 10 level hardware. So in this example, actually adding internal data adds 3 extra slots to the interpolators between the vertex and fragment programs. So it's not a good idea to include it unless you need it. Yes?
On the cutout shader, is that 1 bit, or do you have anti-aliasing on the mask?
It is 1 bit. It's on or off in this case.
The question was on the cutout shader, is it 1 bit or can you have anti-aliasing on the mask?
Yes. No, the cutout simply discards any fragments that fail the test. If you have there's such a thing as alpha to coverage, but it's not easily supported in Unity, even though it does exist. There's some posts on the forums and some documentation online about it, but what that can do is it can actually use a MSAA texture to make the edge a little bit smoother and nicer.
And if I remember correctly, alpha coverage is only on ATI cards. Only
Maybe.
supported on ATI cards. So
If you do want nice smooth edges like that, it's actually better to use some form of transparent shader, but only use that in that area rather than on the whole mesh. Yes.
It's actually a question from the IRC chat. Do you guys support Texture 3D or
Um,
plan to support it anytime soon?
Yeah, the question is, do we support Texture 3D? And the answer to that is, I think internally our API supports it, but it's not exposed. So it's something we could look at doing in the future, I guess. Or-
yes, I mean this is neither of us are actually graphics programmers at Unity, so we would not be the ones exposing it. We're both talking to you from experience of using shaders in past whenever we used Unity. So
yeah.
we'll bring this up with the graphics team
Yeah.
to see what will happen.
3.5.
It's not planned for 3.5, no. If you go upstairs to the hands-on labs and sit down with one of the graphics programmers and really push them, you may be able to get some good results. Yes.
Are there any particular functions that are inaccessible if you have like just standard Unity, not Unity Pro?
The question is, are there any functions that are only available in Unity Pro versus Unity Standard? Not at a shader level, really. There's some functionality that's not there, but things like render to texture and using grab passes, which is where you use a pass to, say, grab the background and do distortion overlays and things like that. They're not supported in Unity Standard, but for the most part, everything is. So there's nothing disabled apart from not supporting render to textures. Yes?
These all seem to be pretty standard shaders you've been showing us. Is there anything you can show us that's kind of funky or crazy, or like why would we want to program shaders?
Okay, that's a good question. Do you want to take over here? I might actually pull my laptop out and I can show you some funky shaders if you're interested.
Okay. I mean, to answer that question on just at a higher level, these are, yes, the very, very basics, and you can do whatever you want to with these things. I mean, I can just go into here and just say, I don't know. I mean, with the spec color, it's already kind of a funky shader, right? You can create a soldier that looks like he's poisoned with a simple specular type thing. So, I mean, it's already something that you can just kind of play around with. And with shaders, it really is a matter of just multiply color in there and see what it looks like. And I don't know, multiply some two textures together based on some color, or interpolate some two textures together based on some color. It really is just a matter of just like play around with it and see what does interesting effects, and then you'll be surprised. Any more questions? Yes, over there.
So how do you go about tying the cutout to like a world position?
Okay, the question was, how do you go about tying the cutout to a world position?
What you'd have to do that is so it uses the alpha value for the cutoff. So you'd use the world position to calculate if you wanted to cut off or not, and then write a value less than the cutoff to the alpha channel.
Yeah. Over here?
Are there certain functions or procedures within C programs that we should stay away from when dealing with mobile devices?
With dealing with what?
Mobile devices.
Mobile devices.
Yeah.
That's a good question, and that's probably not something either of us can really answer that well. I mean,
If I was using mobile devices, I'd probably try and steer clear of surface shaders.
yeah, I mean it's well, if you take for example Shadowgun, there's no dynamic lighting in that period. It's just like when you're on mobile devices, you want to make something look awesome. You just stop using dynamic lighting, and you just hack the hell out of it to make it look interesting. So yeah. Okay, so he's gonna show you some awesome here.
Some shaders.
Let's see if we can make this work.
Yes.
More questions? Yes, over there.
Sort of follows up with that last question, but I love the gem shader that's provided by Unity, but it doesn't work on iOS for some reason. It fails at the runtime. I'm just wondering if there's a way to fix it, or
I'm not familiar with that shader. I know what you're talking about, but I don't know what exactly it's doing. I'm guessing it's doing some sort of grab pass, and I don't know if that's supported on iOS or not. So, yes. Okay, answer his question. Yes. Do that. Oh no. Unity quit unexpectedly. That's not good.
Yeah, I know. It's okay. Let's have a look. Okay, so there's a lot of sort of crazy things you can do with surface shaders if you invest the time. So what we've shown is basically an introduction to shader programming, but there's a lot of really cool things you can do. So I'll show you a few completely procedural shaders that can be written using surface shaders and shader extensibility that don't normally, or which you won't normally see in a built-in, because they're quite custom, and you'd use these in specific instances in your game where you want to do something a bit different and a bit cool. So here's an example of what I call the hypnotic shader. This is completely procedural. It has no textures or anything like that. And it's quite crazy. What we do for this one is we actually basically use the UVs from the mesh that's passed in to generate a gradient. We then use sine waves, time nodes, and panning to animate that gradient, and then using some sort of offset into those nodes, into those sine waves, change the color. So as you can see here, it sort of pulsates a little bit and the colors sort of go out. You could use something like this or a similar kind of technique for animated water, dynamic normal maps, things like that. And it's all they do is quite cheap actually. This one's only 14 shader instructions, for example. That's probably because it doesn't actually use lighting. It's actually auto-generated, so it's probably not the cleanest code ever. But let's have a look.
Could you guys repeat the questions?
Oh, okay. He wants. We're going to load up the code for this shader so we can see what it looks like. So if you just hold on a second. Yeah, so as you can see, it's not the nicest looking shader code ever, because all this has just been filled in procedurally by the algorithm used to generate the shader. But what we have here is we have a custom lighting model filled in. We also have a custom vertex shader for extracting the mesh UVs in a raw manner, which is here. And then we have the surface shader itself, which in my opinion isn't human readable, because the nodes aren't really named anything nice or displayed. But as you can see, it does some calculations on the mesh UV, does some power equations and some sine and some time stuff, like so. And in the end, you get the effect. So this is the kind of thing I actually prefer to use a shader editor for rather than doing it manually, because it's much more explicit and easier to see. There are a lot of other things you can do. So similar to the cutoff example we saw earlier, you can actually do things like vertex modification. Here we are. So this is using vertex shader extension ability in Unity. We should actually, do you want to load up the website and go through some of those, Sean?
Yeah, we can do that.
Yeah.
We have to
change it over.
Hop over here.
We're actually hoping for some questions on image effects if anyone wants to ask any. So
He's hoping. All right, so let's see if I can find something here. Where is it under? It's under reference menu, right?
Yep.
Reference. Where is it? Do you remember?
Go. Surface shaders. That.
Surface shader examples. Here we are. Okay. Thank you. aligned. There we go. All right, so we got a few different examples here, and you notice that some of these are actually very similar to the ones we had. Let's see, we have,
Probably the next page is where the interesting ones start.
well, we have rim lighting here, and then we have world space texture mapping, the cube map one we did. And this is actually the cutout versus world space. Somebody else is over there. Oh yeah, Fat Soldier. It's pretty cool.
This is a good one.
Yeah, so if we take a look at Fat Soldier here, you notice that you can also have your own vertex. Let me zoom in here. Oops. That's the wrong one. We want this one. Here we go. So the bolded text is what's been changed. The other stuff we've already been over. But we have an amount properties here called extrusion amount. This is what's going to get exposed. It's just a range from -1 to 1. And then we have this new vertex program. So we define that we're going to have a custom vertex program. So we do things on a per vertex level. And we say that the custom vertex program is going to be called vert. And that's called vert down here. So we have the uniform from the property above. And then we have this this in-out app data full V. So this is the struct that's used to pass data to and from the vertex program. And what we want to do here is we just want to modify the vertex position by its normal times the amount. And that's just making him fat or making him really skinny, extruding along the normals basically, if you're familiar with modeling programs. Any other specific questions while I'm just going through this? Yes, over there.
What was the program you used before, and is it available?
That's the Strumpy shader editor. That's this guy.
Yeah, it's for free
wrote.
on the asset store.
Any more questions? Yes. Yes. So the question was, if you extrude verts out on an edge, then you get separated planes. And the reason that, and is there a way to avoid that? The reason that's happening is because on hard edges, if you ever go create in your modeling app and you say you select an edge and select harden or whatever, or however
no
it's said.
smoothing groups between the two.
Yeah, or no
basically.
smoothing groups if you're using Max. I don't know why you would ever use Max, use Maya. If you do this, it's actually duplicating that vertex or those vertices along those edges. And there's actually two verts on the exact same spot, one with the normal pointing one direction, one with the normal pointing the other direction, and it's creating tries off of those to do that. And whenever you extrude it, it's going to extrude apart.
So if you want to do something like that, you need to basically make the whole mesh one smoothing group, or soften all the edges if that's the Maya terminology.
Yes, yes.
Yes. So they'll share vertices between all triangles that line up.
Questions? More questions? Is there questions over there?
Yes. You first, and then we'll go to that.
You had said that if it's a hard edge, then there's two vertices and one position. Does
Yes.
that mean that there's, in Unity, there are actually two verts there and it counts as two verts?
Yes.
So if you have a hard edge circle and there's more verts there than a softened edge?
Correct. So like a cube has more than just, 8 verts? It has 4 for each side, which is what, 6 times 4, 24. I can do math. So yes, there are actually 24 verts on a cube that you see whenever you instantiate a normal cube.
So if you softened all the edges, would that maybe make the performance better?
It would look bad.
Yeah, but yes, on hardware that's a problem. Like if you're targeting like a GMA 950, a really old graphics card that does vertex transformations on the CPU, then yes. If you're targeting a modern card, it's better to spend time
What
optimizing
will
other
happen
things.
is because you've got all the vertices being the same point, normal will actually point out at an angle away from all the edges meeting, and because of that, the lighting will look quite horrible over the edge.
There's a question over there?
Yes. Questions behind? No? Come on, someone's got questions.
Right over there.
Yes.
Oh yeah, those image effect things. Oh, you want to take this?
You can. It's okay.
I don't. Oh God. Okay, so we have a few, let's just take a look at some of the standard assets thing here. We have a whole bunch of image effects in here. If we go to the game camera, you can see that it already has a glow.
A blur.
Blur, glow. It's the same effect. It's just one's additive and the other one is just replacing. Anyways, we can take a look at this blur effect and just the basics of how it's working. One of the big things you'll notice here is this onRender image callback. And basically, all image effects and post-processing effects are a combination of a script on the main camera and some shaders. The script on the main camera deals with render textures, creates whatever render texture it needs to create, and then renders the scene to that render texture using some material. Or it gets a render texture that's been rendered from the scene, and then renders to a new render texture using some material. So onRender image is a callback that all cameras get if you add it to your script. And what you do is you get a render texture source, which is going to be the render of your scene, and then a destination, and the destination render texture. And you want to fill this out. So this is like an in, and this is an out. And then you fill up the destination render texture, and that is what's going to be displayed. So if I just created a render texture here and just filled it with red and passed that into destination, then that's what we'll actually display into the camera. So in this instance, I'm not going to go in too deep here, but for the blurring, it's creating a couple of temporary render textures. It downsamples the entire scene, and then it renders it a whole bunch of times, offsetting it around. And by doing that, and the rendering part here is in this graphics.blit, and by doing that, it creates a nice little blur. And then it releases the temporary render textures. And this is really important, otherwise you're going to crash Unity.
You'll run out of memory,
Yeah.
basically.
And you can, really the best way to learn about image effects is to dig into those standard asset ones and just play around with them and see what it's doing.
Yep. Do the shader.
Do the shader?
Yep.
Well, the thing is, the blur effect has a shader, but it's
actually
it's
embedded.
inlined, and it's not even like a fun
okay.
shader. It's just what is it? It's adding a whole bunch. It's just adding over and over and over again. So if we go in here, let's say, I don't know, fisheye?
Yeah.
Let's do fisheye. We have these values, we're going to do this. Look at this guy. So this script is pretty straightforward. onRender image, we create materials up here. All we're doing here is just finding this shader, or we have a shader reference here, if we look at this shader. And we just create a material from that shader. Just create a new material in the scene and apply that shader to the material. What are we doing here?
We're setting.
Yeah, we're just setting some stuff up.
Yeah, explain how that works, John.
So explain how it works.
Okay, so in Unity, when you have a material, if you
the
see,
set vector.
yeah,
Okay.
what you have is in the material editor itself, you can see that. Where's a good example on the soldier? So, for example, here we have these colors that we've exposed and the textures. There's actually an API which you can programmatically use to set these colors. So over the lifetime of an object, you could say change its color from red to green or anything similar to that. It's exposed on the material itself. So in this example, we're setting a vector called intensity, and we're just doing some pre-calculation on some of the values that exist on this script and passing it through.
This is one of those times when you can have a uniform inside your surface shader, but not a property that match it, because you're going to be setting it from script. This is one of those silly AKA advanced times.
Yes. You can also set a property as well by the same API.
Yes. If you have a property and you just want to set like the color directly from the API, you can do that. Though there is already let's say fish, all caps. We can do fisheye material dots. Oh, it's not. There we go. Color, which is just shorthand for dot set vector.
Set color, actually.
Set color with the color. So this graphics.blit is the part that renders the thing. So you pass in the source color, or the source render texture, pass in the destination render texture, it's going to output to this, and then you pass the material you want to use to render. And that's how simple it is. And then within this fisheye material, let's look at the shader for it. Yeah, you can talk about this.
Okay. So unlike surface shaders, image effects shaders don't use, they use ShaderLab obviously, as you can see by the outside, but they don't actually use the surface shader paradigm. The first thing we have is, this is a little bit more advanced, is a CG include block. We saw the CG program block before for surface shaders, but what the CG include block is before every subshader, this block will actually get inserted. So
it basically just allows for reuse of code.
yes, exactly. So the first thing we do is we define a vertex to fragment structure. That's what this stands for. This is like the vertex input structure we saw in some of the other, in the vertex example. The first thing you see is this means we have a position and we have a UV. Now in Shaderland and in graphics hardware, there's certain registers that exist. There's like, for example, the position register, the texture coordinate registers. Depending on the graphics hardware, there's a different number of texture coordinate registers. And there's also color registers and a few other small things like that. So what we're doing here is we're defining a structure that outputs from the vertex shader, and it puts the position that you output into this hardware register. So the pixel shader can use this value from this hardware shader or hardware register.
So this surface programs, the surface shaders that we were talking about before, kind of hides all of this. Normally you would create a vertex fragment program for all types of shaders that you would ever do, but this is the kind of stuff that Aris was talking about when he said, like, this is just stupid. People should not be having to do things like this just to describe a material surface. So this is kind of the stuff that we're trying to hide with surface programs. But unfortunately, surface programs really only make sense for lit materials. And for image effects and things like that, we still have to use this type of shader.
Mm-hmm. Yes. So as you saw before, when we did the graphics.blit, we had a source texture, which was the render output from the scene. This gets implicitly bound to the main texture if you're using image effects, or just graphics.blit will use the main texture, like so. And also you saw the intensity that we were setting before. If you look at the top, we don't actually pass intensity in as a property, because you don't need to do that if you're doing a sed vector. Yes, so like so. The first thing we do is we have a vertex program. What this does is we're doing everything manually now. So there's no niceness that you get from surface shaders. We have this input structure, which is app data image. This is an inbuilt Unity structure. There's a few that are available. So there's ones for meshes, there's ones for full UVs and tangents and normals and all that kind of thing. But for this simple one, what it does is it actually, each vertex gets translated. So you're rendering a square, each vertex will get translated to the corners of the screen in the exact right position for a full screen overlay effect by using this, like so. And the UV will get set up correctly, so it goes from 0 to 1 in the correct order. Now for the interesting part, or the more important part, the fragment shader just simply does shading like you would normally do in a surface shader, but it just calculates things a little bit differently because you don't have these built-in variables to use that you get with surface shaders. So for example, depending on what you want to do, you can do different things, obviously. Yes. So that's the include.
And this fragment shader, the way it's doing a fisheye effect, is it's just offsetting the UVs. Like you get a texture in that's the source texture, and as you move over the UVs, you actually just offset it a little bit. Yeah, and the closer you get towards the center, you offset it even more, and that's kind of how the fisheye.
The center is correct.
Whatever, you get the idea. It's just offsetting UVs.
Yeah. So that's basically.
Yes.
The source texture in this case would just be a picture of the screen, right?
Yes.
Yeah. Oh, the output from rendering the scene. gets
And
passed
the
in.
question there was the source texture in this case is just the picture of the scene.
Yeah.
And I said yes. He said yes.
And as you see, we have a subshader. We don't actually do much in our subshader because this CG include block will get included in front of every subshader. If you have a look here, we set up some properties. So this is a little bit more advanced as well, but this sets things like depth testing, if the shader should write to the depth buffer, if anything should be culled. So in this example, we don't want to do any of that. So we actually z-test. This doesn't make sense for this shader because it's writing a screen space quad, but we don't want to cull anything from the screen, for example.
So a quick question over here.
Yeah, super basic. I was wondering if you could just explain the relationship between image effects and shaders. So are shaders a type of?
Okay, so the question is, could we explain the relationship between image effects and shaders? And the relationship is an image effect is a script on a camera that often uses a shader for rendering, for doing interesting or transforming the texture in some interesting or weird way, depending on what you wanted to do. In color correction, all it does is there's some shader that, based on the color that it sees, decides to pick a different color. Sometimes that's based off of a ramp, some ramp texture that says sample based on the intensity of the color or the hue of the color or whatever, and various other reasons. I mean, that's what an image effect is related to a shader. So a shader is almost in most of the times used for image effects, but that's not the only thing that is necessary to make an image effect.
Yeah. I just also noticed that it's z-test always, not z-test never. So this means the z-test will always pass. So that's why it's there. Sorry.
So that does make sense.
Yes. Yes.
So you mentioned that when you're setting a vector in script, you don't have to define any properties in the shader.
So the question was, if you set a vector from script, you don't have to set up properties from the vector.
Yes.
Or from set.
No,
Okay.
it's not going to. Is it okay to set it in the properties as well? The answer is yes, it's okay. And I actually prefer to do that because it allows you to modify it basically on the material sliders or however you set it up. It's probably better to do that because it gives more usability. The only reason you'd hide it is if it's something very specific which you need to do pre-calculations on or something similar, which in this case we did. The question was on full screen effects, do you have access to the Z buffer? In the shader part? Yeah. Yes, you do. We do it in some of our examples for, say, edge detection and things like, and screen space ambient occlusion.
You have to tell the camera to render it though,
Yes,
like
so
that you expect that you would want this to happen. If you're running in deferred with the deferred renderer, it's already happening. But sometimes if you're running in forward or if you're running on old hardware, sometimes it won't happen. So there's a few different cases where you may or may not get it.
Yeah.
You have to check
It's
for it.
exposed on as a scripting variable on the camera, and if you just set it to depth normals mode, it'll render a depth normals texture, and you can use it whenever you need to.
In some situations where you're morphing the shape of an object inside of the shader,
Mm-hmm.
the need to have more triangles or pre-calculated. I know the hardware is capable of doing that.
Mm-hmm.
Is the shader lab able to support that pre-calculation?
Okay. So the question was, does ShaderLab support tessellation? And the answer to that is currently no.
Well, the question was, does ShaderLab currently support geometry shaders? Basically.
Yes, basically, yes. And the answer is no. Unity is currently a DirectX 9 and OpenGL level, OpenGL 3.2, I think, level engine, and they don't support geometry shaders. Basically, because of backwards compatibility and things, it'd also be very confusing to figure out how to do it. But we're leaving that up to our graphics team to figure out if and when we do graphics, if and when we do tessellation.
There have been talks about doing things like this.
Pardon? Yeah.
There have been talks about doing this. It's just it hasn't happened yet. More questions? It seems like talks are letting out and people are trickling in. So if there are any more questions, we'll wrap it up. If there aren't any more questions.
Yeah, one more.
Oh, the question is there any chance of auto-completion in the shader stuff? And not anytime soon, probably. I mean, there's always chances. There is already a syntax highlighting, but the problem with this is that it's a language that is kind of weird, and it's our own language, so we'd actually have to create this in the autocomplete things ourselves. So unlikely.